All right, so what we're going over today is kind of global wind patterns. Okay, that's going to be distributing solar energy because that's what wind does. It's going to help us do the things we talked about yesterday, which is move energy trapped in the water cycle. Okay, the winds are what's going to move the moisture-laden air masses around. Okay, we're going to talk about why winds come from a certain direction in certain places or have prevailing winds, okay, things like that. Okay, we'll look at all the factors that kind of interact to produce that. And then after this lesson, we're going to move on to specific heat capacity today so that tomorrow we can start latent heat and finish that Monday. All right, so we need to understand how energy is distributed on Earth. We kind of already understand that. What part of the Earth gets the most? The equator, right? Because it's most directly under the sun, okay, and so receives the most intense solar energy. And then, of course, that decreases as you get to the poles. The tilt of the Earth, increases that problem a little bit. So because of that, energy needs to flow from the equator towards the poles. Wind is what's going to help it do that. Wind is an example of which of the three types of heat transfer?
Convection.
Convection, yeah. Okay, little things like that. If you were asked a question on an exam, say about wind patterns, convection should probably be part of your answer. Okay. All right, understanding the role winds play in distributing energy. Okay, we kind of talked about that. First, it's this area is hotter, that area is colder. Second law of thermodynamics, but also part of the water cycle, moving those moisture-laden air masses around. Okay, we need to know what the Coriolis effect is. Okay, you may have heard of that before. We're going to talk a little bit about that today, and know that the global wind patterns we see, or patterns of prevailing winds, are actually the product of both convection and the Earth's rotation. Okay? We sometimes get this idea that the atmosphere rotates with the Earth, but that's not necessarily true. The atmosphere isn't like attached to the Earth's surface. Okay? So the Earth is rotating, but the air is trying to do other things, mostly move north and south. Okay? But the Earth spins the other way. All right? So what we get is some like deflections and things like that. So don't get the idea that as we move along, the air particles in that spot stay exactly along with that section of the Earth. They don't. Okay? The atmosphere is always moving, and it isn't physically connected to the surface. Okay, so the Earth's atmosphere is in perpetual motion, so always moving, even if it's calm, even if we have a day where there's no wind, if we ever get one of those, okay, there's always a little bit of air movement, right? And that's because there's always going to be pressure differences, temperature differences, things like that. All right, so in the northern hemisphere, okay, near the equator, winds generally do this. They come from the kind of east-northeast, right? But from what we just talked about with the second law of thermodynamics, hot air is going to rise and go north, and air from the north is going to have to come in and replace it. So that's going to be moving south. So why aren't the winds near the equator like southerly winds, or northerly winds, sorry? Why does it seem like they come from the east? Because the Earth is moving under its atmosphere, all right? So while the air is actually doing exactly what we described, okay, and that hot air is rising, right, and trying to go this way, and cool air is trying to move south to replace it, okay, the Earth is rotating this way underneath the atmosphere while it's trying to do that. So it makes it feel like it's actually coming from a different direction. Okay? It isn't, but it makes it feel that way. In the same way, if it was a calm day and you're standing, just there, you don't feel any air movement. But if you get on a motorcycle and start riding, does it feel windy?
Yeah.
Yeah. It's not because the air is moving; it's because you're moving through the air. Okay? That's exactly what's going on here. The air may be trying to do one thing, but you're on the surface of the Earth, which is, believe it or not, rapidly rotating, okay, in a different direction. And so you feel the winds being somewhat changed or redirected by that, or deflected by that. Okay? So the Earth does rotate. Okay? The Earth rotates this way. All right? That is why, if we were right here, okay, like on this part of the Earth that we can't see, okay, if we were there, it would be nighttime. But as the Earth rotates this way, the sun would appear to rise in the east, because we would be coming around this direction. And then as we go over the horizon, or over the terminator, okay, they would appear to set in the west. Okay, that's why that happens. All right. Everyone okay with that idea? Okay. So the big thing about the Earth's atmosphere is it is always moving. That's a result of mostly convection, also some pressure differentials. That's why the wind doesn't always come from exactly the same direction. Okay, pressure, high pressure and low pressure areas can contribute to that as well. Okay, so nature doesn't like imbalance. Naturally, nature is always trying to seek some sort of equilibrium. Okay, that's why even in biology, when we talked about cellular transport, most of the cellular transport process, we're trying to achieve a balance. Okay, wind, convection, energy, they're also all trying to achieve a balance. Okay, so we see the movement of air, obviously as wind, trying to balance those temperature or heat energy kind of pressure differentials. Okay, now, one of the most important wind mechanisms on Earth is something called the jet stream. Okay, how many people have heard of that before? Okay, so the jet stream influences weather quite a bit. Okay, and the jet stream is this high altitude wind pattern, okay, almost up kind of near the stratosphere, very top of the troposphere, bottom of the stratosphere. Okay, and it moves very, very fast. Okay, typically it just kind of goes in a bit of a wavy pattern, okay, around this latitude, okay? And it'll go up and down based on differences in pressure and things like that. But it generally goes at that latitude. Okay, it always goes from west to east. Okay, now sometimes pilots will try to get into the jet stream if they're flying in that direction because they'll be able to fly. Yeah, or use less fuel. Okay, fly at the speed they would normally fly at and be more efficient about it because they've got a tailwind. If you're going the other way, you do everything you can to avoid it. All right. If you've ever been on a flight and experienced turbulence, okay, it was likely that you were crossing the jet stream at some point. Maybe it was doing a little bit of a dip and you were flying across it. The pilots will then usually change altitude in order to get out of it. Okay. So the jet stream can be helpful, okay, in terms of air travel, but its biggest role, obviously, is in helping to move moisture-laden air masses around. The jet stream is what helps with the latent heat, okay, that moving water vapor from one place to another, which does transport then thermal energy. Okay, now, like I said, the jet stream can produce different weather patterns, and because it's usually in one place, okay, some places are going to be treated to certain weather conditions more often than others. Okay, this is a very abnormal kind of pattern for the jet stream to make like a figure eight almost, okay, and go back on itself. Most of the time, it just follows kind of like this, okay, goes across there. Right? And this particular day, there were two high pressure areas that were blocking its normal path. It went up and around the first one, okay, and then the second one was pushing chilly, dry air, okay, from the North Pole, basically, down into this area. If this happens in the wintertime, what do we call it? No, the Chinook is warm. This is cold. A polar vortex. You guys heard that term on the Weather Channel? Okay, they use it all the time. Okay, if it's going to drop down like to be minus 30, minus 40 for about a week, I always call it a polar vortex. That's usually a high pressure area forcing the jet stream lower because we get no precipitation during a polar vortex. Okay, it's going to be just cold, dry air being forced down. The jet stream, remember, is going to push moisture-laden air masses from one place to another. If a high pressure area pushes the jet stream away, we're not getting any moisture. Okay? So in this particular one, it had pushed the jet stream kind of up and over and then back out over the ocean. What would it pick up out here? Moisture. And then it pushed it in. So it pushed all this warm, moist air into this area, and it met up with all this chilly air that was being forced from the North Pole, okay, into this same area. Now this is happening kind of in the summertime. What do we call this part, kind of right in between here and here, the United States, besides the Midwest? It has a intimidating sounding nickname. To give you an idea, in case you're not familiar with the geography, we're talking about Iowa, Ohio, Kansas, Oklahoma. This is Tornado Alley. Okay? And the jet stream often follows a path that causes it to be unsettled. through here. Okay? You'll also notice that if this was following a normal pattern, it would also go right through here. You know, the Tornado Alley of Alberta, us. Okay? So the jet stream has a role to play in us getting our kind of seasonal thunderstorm kind of cycle that we get. Okay, so the jet stream, okay, big thing you need to know about the jet stream, kind of a big summary here, okay, is it helps to move moisture-laden air masses and transport latent heat. Okay, that energy stored in water vapor. Okay, so it's a high altitude, high speed wind that moves moisture-laden air masses and helps to transport latent heat. Okay. People who are climbing really high mountains like Everest and K2 and things like that have to be very aware of the movements of the jet stream. Okay? And they can see it when it crosses the top peaks of those really tall mountains. Okay? You'll start to see what they call spin drift. Okay? It's something that they watch for. Okay? So if you got your mountains like this and you're looking at them, what you'll start to see is the snow on the tops of the peaks doing this. If it's on every peak and it's moving in one direction, it means that the jet stream is starting to move onto the tops of those mountains, because the jet stream's position moves around a lot. Okay? If you start seeing that happen, you do not want to climb. Okay? Weather is going to change very rapidly because the jet stream is moving, and if the jet stream is moving, it's bringing something else, usually a moisture-laden air mass and high-speed wind. Okay? That could be deadly if you were trying to climb the top of a mountain. Okay, sort of makes sense? Okay. Meteorologists track this wind. They can see it with satellites. It's very easy for them to track. Okay, and that's why they can somewhat accurately predict what's going to happen. Okay, now obviously it's just a prediction. The jet stream has its own mind. Okay, and sometimes it goes, yeah, I changed my mind. I'm not going to go that far south, and then the prediction is wrong. Okay, and then it goes back north. That happens. Okay, but movement of the jet stream usually signals that there's a change in the weather coming. Okay. All right. Questions on the jet stream? All right. Prevailing wind patterns. Okay. Here, wind is prevailingly from the which direction? East. From the west. Okay, it blows to the east. Okay, comes off the mountains, goes to the east. Prevailingly, the southwest is where we get our winds from. West, southwest. Okay, but typically that's where we get our winds from, right? The reason for that isn't entirely the mountains. Part of it is just the latitude that we are at, okay? This is why latitude can also, it's another thing that latitude can affect, right? Latitude, if we're talking about the four components of climate, can affect light and temperature, but it can also affect where you are in terms of prevailing wind patterns, all right? So for us, okay, we are right about here, okay, in terms of our latitude. We are at the upper end of the part of the world that prevailingly has westerly winds. It's another reason why we have the saying in Alberta, if you don't like the weather, wait 5 minutes, okay? Because we are right at the transition between the mid-latitude westerlies and the polar easterlies, okay? So if we suddenly get a wind coming out of the northeast, bad things are coming weather-wise, right? Because we're just, that's not a hard and fast line, so it shifts up and down, and we're right in that transition area. Okay, so prevailingly in our latitude we get westerlies, but if you go closer to the equator, theirs are typically easterly. Okay, and the reason for that is convection and the rotation of the Earth under that moving air, underneath the hot air rising, cool air descending pattern. Okay, so at the equator, okay, where they get the most sunshine, hot air is going to rise. Okay? Air can't just rise and not have anything come in to replace it, because it would create a vacuum, and those are generally harmful. All right, so what happens is air moves in from the north to replace it. Okay, so vertically, air is doing this, but the Earth is rotating this way underneath it while it does that. So if I'm standing on the Earth while it's going this way, quite fast, okay, I'm going to feel as though instead of the winds coming from the north, which is what they're trying to do, that they're actually coming from the northeast, because as I move through them, they get deflected. Okay? These winds were actually used to have trade between Europe and the New World. That's why they're called the trade winds. Okay? What would happen is that in Europe, they would sail down the western coast of Europe, through Spain and Portugal and all those places, and maybe even northern Africa, okay? And they'd pick up all the goods that they were going to pick up, and then they would take the easterlies, the trade winds, over to the New World, and then they would sail up through the Caribbean and make all of their stops along the east coast of the United States and Canada, and then they would catch the westerlies that would take them back to Europe. Okay? That would be the trade route that they would follow. Okay? Because of course back then there was nothing to power your ship except wind. Okay? All right, does everyone follow kind of how that happens? Okay, so we've got the Earth is rotating, but the atmosphere is trying to do a vertical rotation instead because of convection. Now, that changes when you get further north. When you get further north, there's this air that's come from the equator, and it's cooled and it's trying to come down, okay? But it's still warmer than the air that's up here. So it actually, because there's two kind of conversions happening here, the air actually gets forced northwards instead of south. Okay? So at our latitude, air near the surface is actually being pushed northward, right? But as the Earth rotates underneath it, it actually deflects this way. Right? And so we get westerly winds, or southwesterly winds, which we experience all the time, okay, in these latitudes. Right? It's also why lots of times, if there's a big fire somewhere south of us, we get the smoke. Okay? Everyone kind of follow? Like if there's a fire in BC or southern BC or like Washington or Idaho or places like that, the smoke comes to us because that's typically the direction the wind is coming from. Okay? You probably notice sometimes when there's a fire in Fort McMurray, we get some of the smoke, right? But then the wind shifts and suddenly it's clear again. Okay? That's because we're getting our prevailing winds, which are pushing the smoke back to the north. Okay. All right, is that sort of making some sense? Okay, so here's what you have to understand, okay, and be able to tell me on a test. Prevailing wind patterns are caused by convection and the Earth's rotation. Okay? You need to be able to tell me about how these winds get deflected. Okay? So these two diagrams here, they're basically the same diagram, just drawn a little bit differently. Okay? These are really important. Okay, so you've got to be able to explain that because the equator gets more heat energy from the sun, okay, that air is going to rise at the equator, right, and then it's going to push, it's going to go up, and then air from the north is going to rush down to replace it. And as it does that, the Earth rotates under it, makes it feel like the winds are coming from the northeast instead of straight north, or even more easterly some days. Right? At the next latitude up where we are, okay, the winds at the surface are trying to move north. And as the Earth rotates, they get deflected to the west. Okay? And then at the pole, basically it's the same thing as at the equator. Winds are trying to move south from the pole, and the Earth rotates underneath them. So those are the polar easterlies. We experience those lots of times. We get that northeast wind. We're just getting the polar easterlies during that time because we're so close to the transition between westerlies and easterlies. Okay? Everybody all right with that? All right, I just got to go grab my volleyball here for the demonstration of how this works. Okay? What I use Wilson for is to demonstrate how this happens. Okay? The thing that causes the deflection of these winds is actually called the Coriolis effect. Okay? Now, the Coriolis effect is this apparent deflection of things that are trying to move vertically because they're doing it over something that's moving horizontally. Okay, everyone kind of follow me there? Okay, so I have to basically what I'm doing here is trying to do two different things at once. It's like the moving your hand in a circle on your stomach while patting your head. Okay, so I really have to concentrate. So I'm gonna move this marker straight down the ball, but I'm gonna rotate the ball as I do it. Okay? Now, if you're looking at this diagram here, okay, that's gonna imitate winds. The marker will be the winds trying to move from north to south, okay, and then the Earth is gonna rotate the way it usually rotates. All right? What kind of line am I gonna draw? I'm gonna draw a curve. Okay. Okay, I moved the marker straight down. I just rotated the ball while I drew it. Right? Now, what happens if I'm going north and this one's even harder. And that's hard. I don't know why that one's hard. I can never do that one. I always try, but I can never do that one. Okay, so it will deflect this way. As the Earth rotates this way, if I'm trying to move north, I get this other deflection. Okay, everybody with me on that? I gotta clean Wilson up. Every year I use Wilson and I have to clean him up back there.
You're full of past marks.
Yeah, well, I had another ball that I couldn't clean up and it had like 25 marks on it. It's crazy. I shouldn't have tried to take it off with my finger first. Oh, that wasn't board marker. That wasn't marker remover, that was hand sanitizer. That's for permanent marker. Hello. Should have looked at the bottle. Let that be a lesson to you, always look at the bottle. Oh, by the way, guys, a person in period 2 found this yesterday. Does that belong to anybody? Okay. Okay, so does that sort of make sense how that deflection works? Okay, air is trying to do one thing, but the Earth is doing something else at the same time, and that produces a deflection. All right, it would be kind of like if you've ever been on a merry-go-round, okay? If you try to walk from the center to the edge while the merry-go-round is spinning, do you actually walk straight to the edge?
No.
Same thing, it's the Coriolis effect. Okay, it's two motions trying to happen concurrently, and they produce a deflection. All right, so that's what we see here. Okay, we're seeing again the convection. Okay, these convection cells or Hadley cells. Okay, that are going up and down while the Earth rotates from left to right on the diagram there. Okay, everyone all right with that? So you got to be able to explain that. There'll definitely be a written response question about how do prevailing winds happen. You need to include things like uneven. I start with uneven energy distribution. Okay. Second law of thermodynamics. TD is thermodynamics. Okay. Convection. Rotation. Okay. And then maybe some examples like trade winds. Trade winds. All I do is wind, wind, wind. Here we go. Okay, that was lame. All right, so everyone kind of follow there? Those are kind of your key points, okay, that you would want to touch on if you're talking about why prevailing winds happen the way they do.
By examples, do you mean like?
The trade winds as an example, or the westerlies as an example, polar easterlies as an example. Okay, questions on that? All right. Okay, now that produces obviously bands of wind, right? If we look at this diagram here and the other two that we had on the other page, okay, Earth has 3 bands of wind. Easterlies at the equator, westerlies at the mid-latitude, okay, easterlies again at the poles, right? Earth's atmosphere is transparent, so we don't really see those winds unless there's some clouds that we can observe moving along those lines, and we do. Okay, if you ever watch a hurricane track, okay, you can totally see exactly what it's doing. It's coming up into the mid-latitudes, okay, and the mid-latitudes are trying to force it onto land, okay, and that's when it dies, right? It's trying to go south to north, okay? But it gets deflected and it tries to go this way and then just dies out. All right, everyone okay with that idea? Okay. So we can actually see that, okay, on planets where the atmosphere is more visible. Okay, so in any of the gas giants, especially Jupiter, okay, so the equator would be right here, but if you actually watch a video of Jupiter, okay, you can actually see the bands going different directions, but Jupiter's a lot bigger, so there's more of them. I might even be missing some here, okay? That's part of the reason why the red spot lasts so long. It's so big that it actually touches both sides of that band. So if it's, I can't remember which way it rotates, but I would assume that we would have these near the equator going this way, and the winds on this side of it going this way. Well, you got opposite sides being pushed in different directions. Of course, that's going to keep it spinning, right? And you can actually watch all those little white storms, all those little smaller ones that you can see, they all get pushed different. You can watch them move along that band of wind if you ever watch like a video of Jupiter kind of doing its thing. Okay, this doesn't work anyway, so I'm not going to put it on. All right, everybody okay with that idea? All right, so the Coriolis effect is what I just demonstrated with Wilson there a minute ago, okay? And so what we see is if the winds are moving from north to south, they get deflected, okay, to the west. We actually call that an easterly wind because winds are named for the direction they come from, not the direction they're going. Okay, so easterly winds come from the east. Northerly winds come from the north, okay, that kind of thing. If we're at the mid-latitudes, okay, then we see a deflection going this way. All right? Everyone all right with that? Okay. So as long as you understand and can explain to me that the Coriolis is a deflection that is experienced because of convection doing one thing and the Earth's rotation doing something else at the same time, and that you can tell me that near the equator, that deflection creates easterly winds, and at the mid-latitudes, it creates westerly winds, you're good. Okay? You have to mention convection, because that's a big part of it. The Coriolis effect wouldn't even be there if the air wasn't trying to do one thing while the Earth spun underneath it. Okay? All right, questions on that?
So how exactly does convection relate to that?
Well, you wouldn't get a deflection of the winds if the winds weren't trying to move north-south because of convection, right? The hot air is rising here and then moving northwards, but air from further north has to move in to replace it. So you've got this air moving from north to south that's being deflected. It's the convection winds that are being deflected by the Earth's rotation. So the Coriolis effect wouldn't even be present if the air wasn't already trying to do something else. That make more sense? All right, I'm going to give you about 3-4 minutes. Okay, just write some quick answers to these questions, then we'll go over them. Then we're going to move on to specific heat capacity. Like I said, that lesson's a short one. All right, let's quickly talk about these here. So, what's the effect of unequal distribution of thermal energy on Earth and on the temperature of the atmosphere? Well, if it's unequal, it's going to try to balance, and that's going to require convection, also known as wind. Yeah, I mean, when it comes right down to it, it's going to cause winds to blow, because convection is going to occur. Okay? The second law of thermodynamics is that. It is a law. It is immutable. It is just going to happen. Okay? All right, explain how the Coriolis effect influences the direction of winds in the northern hemisphere. All right, if wind is trying to move from north to south, the Earth will rotate under it, and it will be deflected. If it is moving south, it will be deflected to the west, okay? Which means it'll feel like an easterly wind. If it is trying to move to the north, then it'll be deflected east, making it feel like a westerly wind. That's all you have to do. Okay. All right, what are the trade winds? Okay, trade winds are equatorial, what direction? Easterlies, yeah, they're easterly winds, and they are easterly, again, because of the Coriolis deflection of air moving from north to south. All right, and what are jet streams? Jet streams are high altitude, high speed winds that can move moisture-laden air masses around, helping to transfer latent heat. from place to place. So if you are asked a question about how Earth distributes its energy, should you talk about both convection, prevailing winds, latent heat, and the jet stream? Now, those are the mechanisms through which energy is transferred around the Earth, so they should all be included in an answer about transferring energy. Okay, any questions on those questions? It's like thinking about thinking, questions on questions. Okay, well, let's move on to heat capacity. Okay, so the reason we go over heat capacity is it is involved in Chemistry 20, okay, at least the mathematical part of it. The reason we go over it in Science 10 is to introduce you to the formula, which is super easy, okay? And also because this relates to one of the factors that affects climate. Specifically, it relates to the effect of being near the ocean. Water has a very, very high specific heat capacity. Okay? As a result, it can gain or lose a great deal of thermal energy while barely changing its temperature. Okay? So something that heats up very quickly has a very low specific heat capacity. Metals generally have very low specific heat capacities. That's why we use them for cookware. Okay? It's not going to take a lot of energy to heat up the pan, and thus whatever's in the pan will cook fast. Okay? Like I have two different sets of pans at home. Okay? I have one frying pan that's, it's got to be made of like copper or something like that, and I got another one that those Costco ones that look like rocks. That thing takes forever to heat up. Okay? I'm got something burnt in one pan before the other pan's even starting to, make something sizzle. Right? One has a much higher heat capacity than the other, which leads to my frustration most of the time, and it's staying in the cupboard instead of the other one. Okay, so heat capacity deals with how much energy is required to change the temperature of something. Okay, so for water, a lot of energy is needed to change its temperature. But for metals, very little energy is needed. Okay, there's actually lots of, you've got a list actually in your workbook of all the different heat capacities. Okay, there's got to be a few dozen of them anyway. Okay, so you can see that some things are going to be able to heat up quickly, and other things are not. Okay, so we're not going to deal with heat capacity very much. Heat capacity is when you're dealing with an object, which could be made of a bunch of different materials, so it's kind of an average. Okay, we're going to be dealing with specific heat capacity. Now, specific heat capacity is a physical property. That means every material has a different specific heat capacity, right? Just like when we were doing that lab way back in chemistry where we were trying to identify the unknown compounds based on their physical properties, this is a physical property. It would be unique or specific to each material. Okay, so every element, every compound is going to have a slightly different specific heat capacity. All right, so when it comes right down to it, it is the amount of heat required to raise the temperature of 1 gram of a material by 1 degree Celsius. Okay, so its units are joules per gram degree Celsius. Okay, the amount of energy needed to heat 1 gram by 1 degree Celsius. So the units are joules per gram degree Celsius. Okay, the formula that we'll use to solve specific heat capacity problems is E equals M times C times delta T, right? Where E is the energy in joules, okay? M is the mass of the substance, and that's in grams, okay? And delta T is the change in temperature, okay? And that is in degrees Celsius, okay? C is the specific heat capacity. its units obviously are joules. That doesn't look like a J. Joules per gram degree Celsius. Okay, what does delta mean? Right, so it'll be final temperature minus. Right. Right, is that going to be a relatively easy formula to use? Yeah, everything is multiplied, right? It's all in a line. So if I wanted to solve for m, what do I do with c and t? Just divide them over to the other side. If I want to solve for delta t, I divide m and c over to the other side. Okay? It's a super easy formula to use. Just leave whatever you're looking for on the other side and divide everything else over. Okay? Probably one of the easier formulas we've ever had to use in this course. Okay? Really, really easy. All right, everybody okay with that? So just like we do every time I give you a new formula, we're going to go through a few that are an example of each manipulation, and then I'm going to have you work on a few on your own here. Okay? All right, give you a minute to get that one written down, and then we'll walk through it together. Okay, so just like any other problem we've ever done, okay, you want to write down your givens. So it's asking how much heat. What part of the formula am I looking for? E, yeah, so I'm looking for E on this one. Okay, is needed to raise the temperature of 150 grams. What did they give me there? Mass. Okay, of water, whose specific heat capacity is 4.2 joules per gram degree Celsius. Okay, from 5 degrees to 85 degrees Celsius. So what's delta T? 80.
Are we gonna need to memorize this specific heat?
Absolutely
capacity?
not.
Okay.
If you need one, I will give it to you. Okay, and they're also, for this unit anyway, in the workbook. They're in the, like the second page or something like that is the table of them. Okay, so we're going to be using, obviously, E equals MC delta T. We don't have to manipulate it for this one. We're just plugging in the numbers. 150 grams times 4.2 joules per gram degree Celsius times 80 degrees Celsius. Okay, so I'm plugging in those units here just so you can see that the grams are going to cancel, the degrees Celsius are going to cancel, and I'm going to be left with joules. Okay, I should have fired up my calculator before. What does that come up to, guys?
50,400, I think.
50,400? That seems about right. Oh, now I have a calculator, so now I might as well just do it. 150 times 4.2 times 80. Okay, 50,400 joules. Okay, questions on that one? So that would probably be a 4-mark question. You'd get one for your givens, one for picking the right formula, one for plugging in your numbers, and one for your answer. Okay. Okay, write this one down and give it a try. All right, then I'll go through it with you here in a sec. Okay, so obviously, again, not the most mathematically challenging question you've ever done in this class. Okay, we're looking for the material on this one, so that means we're actually looking for the one thing that is specific to this material, its specific heat capacity. Okay, so we will actually have to refer to that sheet I was talking about, so I should probably bring that up. That is in the workbook. I believe it's the workbook. I had a 50-50 chance. Of course I didn't pick the right one. Okay, so I believe on the first page of this workbook, guys, that's your list, okay, of specific heat capacities. Okay, so if you have that available or printed or whatever, okay, that's it. So let's solve this problem and then we'll refer back to this to see what we're dealing with. Okay, so we're looking for C. We have the mass, it's 100 grams. Okay, we know that it's going to take 4,200 joules worth of energy, and we are raising the temperature from 12 to 62, which is a change of 50 degrees Celsius. Okay, so E equals m times C times delta T. I'm looking for C, so I'm going to divide both sides by m and delta T. So what I'll be left with is this, E divided by m delta T equals C. All right, so that's going to be 4,200, and that's joules, okay, divided by 100 grams times 50 degrees Celsius. Okay, so now you can see where those units come from. Joules divided by grams times degrees Celsius gives you joules per gram degree Celsius.
Do you want us to put all the units?
No, I'm just putting them in there for illustration. You do not need to put them in because you never did before. Okay, so 4,200 divided by, and then the bottom in brackets, 100 times 50. All right, 0.84 is our specific heat capacity, and I believe that's styrofoam, is it not? No, or is it glass? Glass, okay. So glass here is 0.840 joules per gram degree Celsius. Does glass heat up a lot faster than the water inside it? Yes. Okay. Water's got a specific heat capacity of 4.2 joules per gram degree Celsius. It takes less than a joule to change the temperature of glass by 1 degree Celsius. That's why when you put cold water in a glass, you start to see condensation on the outside of the glass. The water's not changing temperature very much, but boy is the glass ever. Okay. All right. Questions on number 2? All right. Number 3, this one's a little bit trickier because it's not asking you for delta T, it's asking you for the final T. Okay, does that really make it a whole lot more difficult? No, it's just going to add one more step in the end. You're still going to solve for delta T here. Okay, so I'll give you a minute, give that one a try, and then we'll look at it together. So we know that iron's got a specific heat capacity of 0.460, okay, typical of a metal, a very low heat capacity. It's going to heat up very fast. Okay, and we know we have a mass of 185 grams. Okay, and the initial temperature is 7 degrees Celsius, and there are 200 joules of thermal energy being used here. All right, so E equals m times C times delta T. I'm looking for something that's part of delta T, so I'll solve for that first by dividing both sides by m times C. All right, so we'll have our 200 joules, okay, divided by 185 times 0.460. All right, that'll give us our change in temperature. So 200 divided by 185 times 0.46. All right, 2.35 degrees Celsius. All right, that's how much it changes by. If it started at 7, what's it going to be now? 9.35 degrees Celsius. Okay, not too tough. Right. So TF then would just be T initial plus the change in T. Okay, no different than any other delta calculation we've done before. Questions on that one? I don't think I did one where you had to find the mass. Oh. Okay. What I would like you guys to do right now is let's have you try the ones that are circled in blue. So let's try 3 and 8 for right now, and then I'll scroll up so you can try some of the other ones. Okay, so this one here, this is the one that's ridiculous, right? Like if paper got that hot, it would be on fire.
No, it's just
Oh, not getting it? Okay, so 28 joules of energy, so we know what E is, right? E is 28. The paper is a mass of 0.01 grams, and paper's heat capacity is 1.800. So if we're looking for delta T will be E divided by M times C. All right, so that'll be 28 divided by 0.01 times 1.8.
I think I found the issue.
Yeah, if you don't bracket the bottom.
It's not the bracketing the bottom. It's that I was getting like one digit off. I was like, what's going on? And then I realized just now I did 0.1 instead of 0.0.
Always something simple. Okay, yeah, and so it's, sorry, number 16, I think that's supposed to be 4,762, because it's 4,761.9. I was making up the key too fast and I was being sloppy. Okay?
Yeah, and then 14, it's like 13.7, I think. Like it's 0.13.7. So
Yeah, so again, it's around. That was just me making up the key too fast. Okay, questions on any of those? They're pretty straightforward. Okay, so like I said, there's two reasons we need to learn this. It's part of why oceans are a factor that affect climate. It is something that continues on in Chem 20, and it's going to be part of what we do tomorrow with latent heat. Okay, so tomorrow we'll start latent heat and the heating curve of water, and we'll finish that up on Monday, start biomes right after that, finish biomes Tuesday morning, okay, and in the second half we'll do our unit exam review.
Do we have a quiz?
No quiz, no more quizzes, we're all done with quizzes. We have no time for quizzes now. Okay. All right, good job today, guys.
Sorry.